Welcome to Masterpiece Statistics with Michael. Today's topic is multiple regression. So we're going to look at a data set that we talked about during the lecture. And the question we're asking is, do SAT scores and high school GPA predict college GPA? And I've got a data set right here that we can look at. There it is in Excel. So these are my college GPA scores. They're going to be the variable that I'm trying to predict. They're going to be the y in this. And here are my high school GPA scores. So that's one of my predictor variables. You can see I'm just scrolling down. And then my other predictor variable is going to be SAT total. I took out letter quality because we saw that it wasn't significant. So I went ahead and graphed the bivariate data. So you can see that the thing I'm trying to predict, the college GPA, is on my y-axis. And here I have high school GPA on the x-axis. And you can see the correlation is, pretty fair. It's got a good magnitude. The actual correlation is 0.496, but you can see it's not perfect. The data points are spread from the line. I used R to graph this because R is the statistical program that I use. But we're also concerned about the relationship between college GPA and total SAT score. So I've graphed that here as well. You can see college GPA is on my y-axis, total SAT score is on my x-axis, and you can see the correlation is actually pretty similar. It's 0.52 for this one, and you can see it's not a perfect correlation. It's positive, it's sloping up, but my data points aren't all falling on the line of best fit. Now, when we do regression, there are some assumptions we have to check. I'm not going to do that here. I've already done it, so you can just know the assumptions of regression have been met here, and we can just move on to get a general idea of what we're doing. So we graphed the bivariate data, but that's not all we're interested in. What we really want to know is how these things work together to make a plane of best fit. So I went ahead and graphed that for you. And now you can see this awesome cube where we can see a three-dimensional plot of our college GPA data. And you can see that the SAT and the college GPA slope is the orange line, and then the blue line I put there is the high school GPA and college GPA slope that we're looking at. So this is awesome. And now we can kind of get an idea of how our points fall away from the plane of best fit. But wait, there's more. I also graphed this spinning three-dimensional representation of our data and the plane of best fit. And I'm just going to say here, I'm going to let you finish SPSS, but R is the best statistical program of all time. And this is why. I'm not even very good at coding, but look what I can make. So anyway, this is how we can see if our prediction with these two variables of college GPA were perfect, then all of these points would fall on this plane. But you can see there's some distance, and they're drawn with those lines from the point to the plane, and those are the residuals. This is their new measure of error if we're predicting college GPA with our two variables, high school GPA and total SAT score. So here's our data, and now we want to figure out what's our new measure of error. So there's my college GPA scores. These are our actual Y values. And over there you can see the fitted values. Now, these are the Y values on the plane. Recall that a line has two coordinates. It's going to have a Y value and an X value for each point on the line. With a plane, we're going to have three coordinates. We're going to have an X value, a Y value, and a Z value. These are just the Y values for my fitted plane. If I were to run my cursor along the plane, we'd see all of these values show up for Y. So to get my new measure of error, I'm going to subtract these fitted Y values from my original Y values, and that's going to leave me with what we're going to call the residuals. Then to deal with the issue of negative, we're going to square those residuals, and then we're going to sum them. Scroll down, you can see I sum them, and my sum of the squares is 34.61, and this is my unexplained variance. In other words, this is the distance of my actual values from their new predicted expected value, and that predicted expected value is the plane of best fit. And I want to compare that value to the previous value of error that we found. So the way we did that before was we said, what's the difference between the y values we have and their expected value with no predictors? And that was the mean. So when I compare those two values, that's going to help us understand our explained variance. So let's see how we do that. So we're going to look at our y values, that's college GPA, and we're going to subtract from them the previous expected value. And with no predictors, that's just the mean. So our mean college GPA is 1.98. That's shockingly low to us because we're graduate students, but this is real life. And so when we subtract those mean college scores, it's the same score from every single y value of college GPA, we get our old residuals, and this is just basically the variance that we had before in our distribution. And so there are residuals. Again, to deal with the issue of negatives, we square them, and so now we have only positive values, and you can see that I summed the squared values, and that's our measure of total variance. We can also call it the old measure of variance that we had when we didn't have any predictors. So now we want to say, what's our r squared? In other words, what's the proportion of estimated error that we save with our prediction? So our current estimate of error is 34.61. And our previous estimate of error with no predictors was 55.57. And so now if we subtract 34.61 from 55.57, we get 20.962. That's how much error we're saving. We call that our explained variance. And then if we divide that number by our previous estimate of error, we get 0.37. And that's exactly what r gives me when I ask, what's the r squared? This is our proportion of variance accounted for. So another way to look at this is to look at two planes within the regression cube. So I plotted that here, and you can see our original prediction plane with our data is in the blue. It's going up because there's some good correlation. But if there had been no effect of SAT total and high school GPA, then the green plane is actually what we would have seen. And that would have meant that no matter what your high school GPA was, your expected value for college GPA would have been 1.98. And no matter what your SAT score was, your expected value for your college GPA would have been 1.98. So you can see that if there's no effect of predictors, our expected value is the green plane, and our variance around that is our error around the green plane. But when we add in that blue plane, now we have a shorter distance from our lines to the blue plane, so we save some error. So here's another diagram of how we can look at r squared. The blue, the light blue, is all of the variance that we're accounting for. In this case, it's about a third, so that's actually proportional to what I drew, though I didn't do that on purpose. And the dark blue is all of the rest of the error that we didn't explain with our prediction line, and that's going to be that 37 number that we saw earlier. It's the distance from our current y values to the fitted y values of the prediction plane. And the entire circle of y is our whole estimate of total variance. So we want to look at a plus b plus c over the whole circle of y, and that's our r squared. That's the amount of variance that's being explained by these two predictors. So now let's look at part correlations, also known as semi-partial correlations. They have two names for the same thing. Of course, that's really confusing, but let's try to stick with it. So let's pretend that we really care about the relationship between the SAT scores and the college GPA, and that our high school GPA is kind of this nuisance variable that we know is correlated both with SAT scores and with college GPA. I'm using this picture to represent high school GPA because you don't get stickers in college. So let's say this diagram represents that relationship. Y is our college GPA variable, and then the smiley face is the variable that we're really interested in the prediction power of, the SAT scores, and then the X kind of yucky face is our nuisance variable, which is in this case high school GPA. So the part correlation says if we can subtract the relationship between high school GPA and SAT total scores from the SAT total score values, and then see what's the correlation between those remaining values and all of the variance in y. Then we're going to be controlling for high school GPA's influence on SAT total scores before we look at its relationship with total college GPA. So I found that the best way to visualize this is not with a Venn diagram, but with a million Venn diagrams. So here we go, and you're welcome. So here is our Venn diagram with just the SAT total values represented. This is the predictor we care about in this case. And so for the first step of calculating the part correlation, we're going to need the SAT total values. And what we want to do is subtract from those total values the variance that can be explained by the nuisance variable high school GPA. And so the only way we can figure out the variance that can be explained by a predictor is to get a line of best fit. So here's our line of best fit when we predict SAT total scores by high school GPA. And what we care about here is the fitted values, which is what are the values of SAT scores on that line for every value of high school GPA. So I calculated those values in R and I put them in this column here. Now recall that for a line, each point on that line is going to have two coordinates, an X and a Y. Here we only care about the Y coordinates. We need to know what are the predicted values of the SAT total scores when we predict them by high school GPA. When I subtract those values from the total SAT scores, I get this minus fit line. So now I can say that I subtracted the variance in SAT total scores that is explained by high school GPA. So now I want to say out of these leftovers, after subtracting for the relationship of high school GPA, what is the relationship between my leftover SAT total scores and all of the Y scores, which is the total variance of Y? And I do that by examining the correlation between those minus fit values and college GPA. So you can see here, scrolling, there it is. You can't see the formula at the top, but if I double click it, it's going to highlight the two rows. So you can see minus fit. Over there is my college GPA, this is my Y scores. And the correlation between them is 0.361, and that exactly matches the output that I got from R. You can see that in the lower corner. And you should note that it's this number in the top right of the part correlation matrix. And the reason it's not the same at the bottom left corner of the part correlation matrix is that I have to do all those steps. It's not the same like a correlation where you can say, oh, the correlation between college GPA and SAT is going to be the same if I put college GPA as the X or the college GPA as the Y. For here, it's different because we have to go through those different steps. So now for the partial correlation, what we're going to be doing is subtracting the variance that can be explained by a high school GPA from SAT total and from college GPA. So again, with the Venn diagrams, here's our first two steps, they're the same, SAT total minus the variance explained by high school GPA. And then with college GPA, we're going to subtract the variance explained by high school GPA. So in order to do this, we need to find the line of best fit when predicting college GPA by high school GPA. That gives me the fitted values for college GPA, and then I put those right there. I subtract those fitted values from the original Y, which is college GPA, and then I get that minus fit column, which just explains the amount of variance left in college GPA once I subtracted the variance that was explained by a high school GPA. So now that I have that, I can compare that to the previous values, the SAT total values that have subtracted the variance explained by high school GPA, and I get the correlation between those two columns. You can see there, they're both highlighted, the green and the blue. And that correlation is going to be my partial correlation coefficient. And it's 0.4163, which we can see is the same as the output that was given to me by R, which is up in that top right corner of that partial correlation matrix. So you'll notice that our partial correlation is larger than our part correlation. And that's because we've taken out the variability in Y that's associated with our nuisance variable. And variability necessarily decreases correlations. So when we remove it, we can increase our correlation. This is just like when we plot bivariate data. When we have data points that are far away from the line of best fit, we have more variability and a lower correlation. But if we can remove some of that variability, our correlation is going to go up. So that's the difference between part and partial correlations. Thanks for joining us today on Masterpiece Statistics.